This is the lecture on technical error measurement, which I think is probably the most boring lecture in the course. However, it's important. We're using a tool that needs a lot of practice, and a lot of people say, "Hey, that's just used to make a dress, to make a suit. That's just measurements for tailors. That's not very serious." But if we want to make these anthropometric measurements serious, we must treat them scientifically. We must estimate our error of measurement. Thereby, when we measure again, we can tell whether that difference or that change, say in 4 weeks, whether that change was significant or it's within our error of measurement. That's one of the uses. So the sources of error in anthropometry are measuring techniques, which we will practice and diminish in the course. And especially you will improve a lot when you do your 20 post-course profiles in that 4-month period after the exam. That's when you get really good at measuring. Especially after the 9th subject you measure in duplicate, you start getting very good. It's like driving, okay? You just need practice. Then there's biological variation. For example, the time of day which you measure, how much food you had yesterday or the day before. If it's a female, whether it's they retain fluids in the few days before the menstrual cycle. So there's a lot of variation. If you just had a shower, a hot shower, or a sauna, or if you just worked out, of course, your measurements are going to be a bit different. Ideally, you will want to measure early in the morning after waking up and going to the bathroom before eating breakfast. But that's not the case of every scenario. Sometimes you just measure when you can, not when on the ideal situation. Well, there is biological variation, which adds error. There are some people that have very tough skin folds. There's some people that have very soft skin folds, and that affects the measurement. And then there's equipment calibration, which we will cover in another lecture, but it is just as important. So today we'll concentrate on the error produced by measuring technique. Now look at these two measuring conditions. This is ideal. Here we are measuring the US rowing team in Australia for the 2000 Olympics, and we're measuring them in broad daylight. We have it doesn't have to be outdoors, but we need a lot of light. We have a lot of light, and the anthropometrist can measure, and she has a recorder, not only to record the measurements, but also to check on the technique, see if the tape is crooked or not. So this is the ideal scenario. We have time, we have enough people to measure, and we have good light and silence. She reads the measurement and dictates it to the recorder. For example, if this girth was 30.5, she would say 30.5, number by number. She repeats the figure as she's writing it down, 30.5. She hears it and confirms. This way you diminish a lot of the errors when you're doing projects where you're measuring a lot of athletes. This scenario, this was actually September 11th, 2001, very sad day for the world. And we measured the youth divisions of Boca Juniors. They said, come on over and measure 27 athletes. When we got there, there were 81 athletes. So we were short of anthropometrists and recorders. So the same anthropometrist had to measure and record at the same time. We had people waiting and talking. This was in the locker rooms. It was dark. It was humid. So people were making fun of whoever was being measured. This is not the ideal scenario. Now, when you're writing down the numbers of the measurements, there are 3 pairs of numbers which can get confusing. For example, look at these 3 numbers. Is that 30.1 or is that 36.1? Is that 29.3 or is that 24.3? Is that 77.7 or is that 11.1? Okay, so those numbers are confusing. The 0 and the 6, the 4 and the 9, and the 1 and the 7. So what's the best technique? The best technique is to write the 6 really closed and to write the 0 really closed also, or you can put a line through it. The 4 has to be very open and the 9 has to be very closed at the top. When you're writing the number 1, it's best to do it just as a single stick and not add anything to it. And when you're writing the 7, it is best to write it with the European crossing to differentiate it from the American 7, which can be confused as a 1. So if you can get into the habit of doing that, I'll tell you, when you're doing a large project, measuring a lot of athletes, these errors can creep in, and especially if you're dictating your numbers to a recorder who has a different handwriting, and these errors can be quite a problem for processing the data, delivering results later on. So this might seem silly, but it's really, really important. Now, it is always best when you have the time to take the measurements in duplicate. That doesn't mean one right after the other. Tricep skin fold means doing the 8 skin folds and then going back to triceps. So ideally, you want 1 or 2 minutes to pass between each repetition of, say, a skin fold. Now, if the difference between the first and the second skin fold or measurement is too large, what is too large? I'll show you now with a table I have made for you that gives you the tolerances or the limits, so you can know when too much is too much. Then you would need to take a triplicate measure, a third measure of that skin fold site or whatever site you got a difference in. And then if you have triplicate measures, you use the median value. The median value is you take away the smallest, you take away the largest, and you stay with a value that falls in the middle. Okay, delete the outer, or you can delete the outlier. So if you have 2 measures that are very similar, one that's complete outlier, you can delete that one and use the mean or the average of the remaining 2. Most likely you'll be using duplicate measures. In that case, you use the average, the mean value, okay? And sometimes if you have a patient or an athlete that you follow them month after month, it's always a good idea, especially in skin folds and girths, to measure them in duplicate or triplicate to see the differences. Bone breadths, unless they're a child that's growing, you can measure them the first time and then keep them for the rest of the measurements. Now, if you're doing a cross-sectional study, let's say you are measuring a team and you want to get, average values per playing position. As you're not going to follow them up, it's just to gather information. Sometimes you have to measure, as was my case in Arizona this weekend, I measured 82 athletes and to get averages. Okay, and you are short of anthropometrists, you're short of equipment, you're short of time, you're given a few minutes for each player. Then what do? You measure single time, okay, and you try and concentrate, and the averages of a large group will sort of make any mistake die out in the average of playing positions. Ideally, you don't want to do those mistakes, but sometimes you do what you can with the time and resources that are given to you. Now, this is a type of biological error. Remember, when you press a skin fold, it's getting compressed. Why is it getting compressed with your fingers and the branches of your calipers? Because you're moving fluids away from that. So let those fluids return by waiting 1 or 2 minutes before you do the second duplicate measure or triplicate measure on that skin fold. This is a study on skin fold compressibility done by Clarice, Martin, and Drinkwater about 40 years ago, where they dissected cadavers, they measured the skin folds on cadavers, then they measured the breadth of the skin fold, and they calculated the compressibility. And for example, the highest compressibility in skin folds was at the biceps and at the supraspinalis sites. Those are very small skin folds. And the least compressible skin folds were front thigh and medial calf. So those are pretty good skin folds because they don't compress as much. But anyway, that's just to keep it in mind. These are some images of the cadavers that were used in that study. 27 cadavers, 22 for the pilot study, 25 for the other measures. They did a lot of information from this cadaver study. A lot of that information is to develop muscle mass equations, body composition systems like the five-way fractionation by Kerr and Ross that we see in level 2. And they also use this information to validate existing body fat equations. So they measure the cadavers, they plug their skin folds into equations to see what the percent body fat was. Then they did the dissection, they got the whole amount of body fat, and they compared, okay, this is the real amount of body fat. How far off were we in our estimation using different equations? So that's an interesting study. Hasn't really been done after that. Okay, and in this study, you had two subjects, like these two subjects, subject 23 and subject 20, that had the same amount of adipose tissue, but their compressibility was completely different. So in one of them, you got very tough skin folds, and the other one, you get very compressible skin folds. So you will make an error estimating body fat from skin folds. That's one of the limitations of anthropometry, especially as we age and our tissues become softer, sometimes harder. Okay, this is another picture of Don Drinkwater, another of the authors, measuring the calf skin fold in a cadaver with a Harpenden caliper. Not the best technique, but it's not easy to measure cadavers. This is another picture where they are using the Harpenden skin fold caliper to estimate the thickness of skin in different parts. And the thickest part is the subscapulary. That's where the thickest skin is. The thinnest part is in the biceps. And males have thicker skin than females in general. So here's the subscapular that has the largest skin thickness. And here is the biceps that has the thinnest skin, and then males have on average a thicker skin than females. However, when we measure a skin fold, we include the skin and the fat beneath it. Now, what is technical error of measurement? Basically, in anthropometry, we're worried about two things. Sure, in body composition analysis, we're worried about validity. I mean, does the equation predict the real amount of fat that is in the cadaver? So you do a validation study where you measure the cadavers, then you cut them up, you get all the fat together, and see whether your estimation is validated by the amount that is in the tissue, the real stuff. Now, accuracy is how close you measure to your instructor, your level 3 or level 4 Isaac instructor. Precision is how close your first measure is from your duplicate measure. So in both, for example, when you hit the target right on, that means that you're both accurate and precise. In the B scenario, you have somebody that's who's very precise. All his measurements are very similar to each other because they have a lot of practice. However, they miss the right target by a lot. That's probably because they never compared their measurements against a criterion measure. That always happens with people that are self-taught and have a lot of practice. They have 20 years practice, but they never had their measurements checked against an instructor. And that's a tough scenario because those guys say, hey, I have 20 years experience. I measured thousands of athletes. You know, I'm not going to do what you say. I measure my way. So those are tough cases a lot of the time. Here is where you should be after the course, after 3 days, okay? Measuring in the right place, accurate, but needing more practice, okay? The precision you obtain from the 20 post-course profiles that you do within a 4-month period after the exam. And here's a case of both inaccuracy and imprecision, okay? So basically after the course, we want to try and get here, and after your 20 post-course profiles, you should be around there. Every 4 years, every 4 to 5 years, you have to recertify your ISAC certification, or you can go into level 2, or you can go into level 3, but every 4 to 5 years, you need to recheck your measurements against another ISAC instructor, just in case you are diverging from the original technique. So this is the way that ISAC makes sure that everyone is on the same page when it regards to measuring technique. Now, there's 2 types of technical error measure, as I mentioned. You have the intra-tester. That means repeated measures of one tester. This is how precise you are. So you measure your triceps once, then you go to the other skin folds, you wait a couple of minutes, then you go back to your triceps, you measure it again. And if these 2 measures are very similar, that means you're very precise. Inter-tester measure are the repeated measures between 2 testers. Ideally, a criterion instructor, level 3 or level 4, against your level, against you that are taking the course. So that's a measure of how accurate you are. And in an ISAC course, we practice both things for 3 days. Then when you're on your own doing the 20 post-course profiles, you're just practicing your precision, because us instructors cannot go to every one of your 20 measures all over the world, even though we would like to. Now, how do you calculate your technical error of measurement? Okay, this is a bit complicated. It's statistics. You don't have to worry about this because I'm going to give you Excel spreadsheets that do it for you. But for those that are more statistically inclined or are curious about it, very briefly, I'll say that the calculation is the standard deviation of the differences between measures. The absolute technical error measurement, say in millimeters for skin folds, is the square root of the sum of the differences between the first and the second measure divided by 2 times the number of subjects you measured. And that some of the difference is squared. And you go, oh, what? What's that? Okay, you square it to take away negative and positive signs, and then you have to bring it back to earth. That's why you square root it. Okay, so it's not that bad. Then you can express that in relative terms as a percentage. So you get this value, the absolute technical error, you divide it by the average, this would be the average of all your measures, and you multiply by 100, okay? That's basically the technique, but don't worry, the software will do it for you. Now, there are tolerances in order for you to pass the ISAC exam and for your 20 post-course profiles. For skin folds, the tolerance is 12.5% error. For other measures, it's 2.5% at the exam level, okay? This is for the differences between the criterion measurer, the instructor, and yourself. Within yourself, your skin folds, you need a 10%, no larger than a 10% error for skin folds, no larger than 2% for other measures, okay? Now, in the post-course 20 profiles, because you're doing more measures, 20, instead of the 3 subjects you measure at the exam, then what does that mean? It means that error diminishes, plus you have more practice. So the error tolerances are smaller. Are they achievable? Yes, they are achievable. If you practice in your course, you pay attention, you correct your measures against your instructor, and you do your work in 20 post-course profiles, you will achieve these tolerances and get your ISAC certificate, which is like a driver's license in anthropometry. There's theory, and then there's practice, the main thing. For level 2, however, the standards are higher. So if you decide to go into level 2, say 4 to 6 months from now, then you will have a lot more practice. So we expect you to have lower error margins. Now, this is the table I was mentioning. It's very hard to go calculating those percentages, as I've explained in that slide, with all those statistical square roots and funky mathematical statistical signs. Now, this makes it easier. Let's say you're measuring skin folds. You measure the first one, you measure the second one, you see that on your pro forma, the 2 values. When do you know if you have to take a third measure because the difference between the 2 is too big? Let's say your skin fold is 10 millimeters and 11 millimeters, okay? So it's between 8 and 15 millimeters. Then if you got a 10 and an 11, that's a 1 millimeter difference. That's okay. You don't need to make a third measure. However, if you measure 10 and 12 millimeters, that's 2 millimeter difference, then I would suggest taking a third measure. If the skin fold is larger, let's say between 16 and 30 millimeters, that's a thick skin fold, like my ab, for example, then the difference can be up to 2 millimeters. And if it's larger than 30, it can be up to 3 millimeters. Now, you have to be very careful in the very small skin folds, like the biceps, like the supraspinale or the calf, or if you have very lean athletes. Say if you have a skin fold of 5 and another one of 6 millimeters, the technical error will say, okay, that's no good. There's too much error. So when you have very small skin folds in the 4, 5, 3, 6, 7 region, I would suggest taking additional measures until you find 2 that don't differ between each other, okay? Now, going on to girths with your measuring tape, let's say you're measuring small girths like the arms or the legs or the relaxed arm or the calf measurement. Okay, the tolerance up to half a centimeter or 5 millimeters. What about the large trunk measures like waist or like hips? The difference can be up to 1 centimeter. So if you get 100, then 101 or 99, that's okay. When you're measuring breaths, okay, if you're measuring the small appendicular breaths, like in level 1, you want a very, very small difference, okay? Only 1 millimeter. So let's say you're measuring an elbow breath and you get 7.6 and 7.5, that's okay. You have 7.6 and 7.4, that's 2 millimeter difference, take an additional measurement, okay? Until you get a 1 millimeter difference. And then you can cross out the outlier or use 3 measures. The large trunk measures that you use in level 2, okay? No, this is not 5 centimeter difference, okay? Yeah, this is okay. This is okay. It's a 1 millimeter difference. So let me get the eraser rate. Okay, so that's a 1 millimeter difference. This is a 5 millimeter difference. That's half a centimeter. That's okay. That's okay for, say, when you're measuring 40 centimeters just by measuring by half a centimeter is okay. And when you're measuring height or seated height or arm span, okay, mostly 1 centimeter tolerance is okay. And if you're measuring a short height like hand length that you do at level 2, then half a centimeter is the upper tolerance level. So this is quite a useful table to have. It's a handy table to have next to your measurements when you're practicing and at the exam, so you can see whether you need a third measurement or not. I'll be helping you with this in the course. Now, there's another measure you'll see in your exam results, which is called the intra-class correlation coefficient. So this is like a correlation coefficient, let's say between your first and your second measure, or between the criterion measures and the student measures, okay? Usually the correlation is very high. It should be above 0.9, and I really haven't seen anybody, except a few cases, that have gone below that. So I wouldn't worry about the ICC, the intra-class correlation coefficient. Now, you will get a spreadsheet where you upload your 20 measures post-course in duplicate or triplicate of 20 people. You have the possibility of printing a result for whoever you measured, with some variables as body fat, BMI, waist to hip ratio, somatotype, muscle mass, skeletal mass. But the main thing is to get your TEMs, okay? So in this column for your measures, once you upload the data on the 20 post-course profiles, it'll give you your absolute value, your percent value of technical error measure. It'll give you your inter-class correlation coefficient that you don't worry about. And you will see the target levels, the target values, percentages for level 1, for level 2, for these measures, for skin folds. And you will also get a graph, a bar graph, where the red bars are the tolerance level, the blue bars are your technical error. So if you happen to see one of the blue bars that goes beyond the red bar, you know there's an error there, that you need to check that measurement. Most likely it's an input data error. You forgot to put a decimal point, or you put it in the wrong place, and that increases the error. So check for errors by using this graph, okay? And if it's not a data loading error, maybe you need to work and get some more measures on the triceps. For example, in this case, so that you need to improve that percent. Now, this is the idea with the ISAC post-course profiles, so that you get proficient in measuring and precision, and you get your ISAC certificate that you download from the ISAC page. When you take the course, I will be sending data of your name, your email, and to the ISAC webpage, and you can create your own profile, and you will automatically become a member, and you can download your certificate after we've checked that your 20 post-course measures are in order. Now, there's another thing you can do, which is calculate your technical error measurement for the sum of 6 skin folds. So these are the 6 skin folds that we usually use. If you've seen my previous lectures, I've mentioned this in 3 of those lectures: the sum of 6 skin folds, triceps, subscapular, supraspinal, abdominal, front thigh, and calf. You can add the absolute value in millimeters after your 20 post-course profiles, and that will give you a value in millimeters of what's your technical error measure for the sum of 6. What do you do with that? There's another Excel spreadsheet that I'll be sharing with you, and it's called the establishing significant differences Excel. What you do is you have your 6 skin folds, okay, and your sum of skin folds. This is your first evaluation. Let's say you do this now in August, and these are the values of one of your athletes or one of your trainees. And then let's say in September, a month from now, you measure them again, and you plug in the average of the following results. And here you can see the delta, the difference. For example, in triceps, there's 0.5 millimeter less. In subscapular, there's no difference. In supraspinal, 0.5 millimeter less. In abdominal, 1 millimeter less. In front thigh, you have 0.5 millimeter more. And calf, nothing. So you had 63 millimeters in the sum of 6. Now you have 61.5. They've lost 1.5 millimeters for the sum of 6. Now, the question is, okay, is that a significant change in body fat? Have they lost body fat? Or is that within my technical error of measure as an anthropometrist? So you have to know what your TEM for sum of 6 is. And you get that from the sum of 6 on the 20 post-course profiles from the previous page. And as I said, it's 1.519. So what does the Excel spreadsheet do? It calculates your confidence intervals, your upper and lower confidence intervals. And what does that mean? It means that with a 68% confidence, the average difference was minus 1.5 millimeters, but it could have been, the difference could have been as high as minus 3.6 millimeters, or it could have been as high as plus 0.6 millimeters, okay? So sure, the average says that I lost a little bit, minus 1.5 millimeters, but the range of my confidence interval goes from losing as much as 3.6 millimeters to gaining 0.5 millimeter, 0.6 millimeter. So you don't know, with a 68% confidence interval, you don't know whether you lost or you gained body fat. Why? Because the difference is very small, and with my technical error of measure for sum of 6, I cannot really determine whether you've gained or lost body fat. So the question is, does the range of the confidence interval include the 0 value? And here, yes, it does, because it goes from minus 3 all the way to plus 0.6. And what is the rule? If the range includes the 0 value, the difference is not significant. So is the difference significant? No, we cannot really say there was a significant change in this person from one month to the other. Why? Because the confidence interval of my technical error measurement for that difference in that subject 1 month apart is very small, and I cannot determine whether he lost fat or he gained fat. The most likely scenario is that he didn't change. So if you're doing a scientific study or trying to see the effect of an exercise program on body fat, or a supplement on body fat loss, or a diet, whatever, you can use this approach to work in your data to see if the differences are significant or not. And you can present this data in a congress or in a meeting. And if people come to you and critique you and say, oh, you use anthropometry, you know, that's not very precise, you can answer, excuse me, I'm a certified level 1 anthropometrist. This is my technical error measurement. And my data has been presented by calculating confidence intervals based on my technical error measure for skin folds. So I can say with a level of confidence that there has been a significant change from this diet regimen or exercise regimen or not. So you use imaging technology, you use MRI scans, okay. Did you use DEXA, use bioimpedance? Did you do duplicate measures on your subject? What is your technical error measure on this machine? Okay, are your differences statistically significant according to your technical error? Most likely they haven't done that. They think, oh, machines are perfect, you know, this is what we do. Machines are great, but you need to use this technical error approach to do proper science, okay? So no one can criticize you if you do the right statistical steps and take into account your technical error measure. Okay, thank you for your time. I'm sorry if this was boring or complicated, but it's a necessary part of the course.